This is lesson 4 of chapter 10. So we are doing changes of state today. We are still discussing states of matter. So we are continuing to talk about the kinetic molecular theory, but we've already applied it to the 3 states of matter. We did gases, then liquids, and then solids. So today we're going to cover states of matter and changes of states and how that works in terms of the kinetic energy. We're going to look at a couple of different terms. Most of them you're familiar with, so it's really not anything hugely new. But we're going to look at some graphs. And then I'm going to show you the lab that you should be performing hopefully tomorrow or whenever the next time is that you're going to be meeting. So changes of state. So you should be familiar with most of the things in this chart. We talk about the state of matter. What we're really talking about there is the phase. Okay, so phase can be another word for a state. So a phase is any part of a system with uniform composition and properties. So that means that like if you have ice, water, you would have 2 phases there. So you would have the liquid portion of your water and then the solid portion. So you have 2 phases. If you have anything that you've dissolved in something else, if not all of it has dissolved, like salt water. Okay, if you've dissolved salt into water, you would have, if you dissolve all the salt, you have 1 phase, okay, because the salt is all dissolved. But if you have some solid that hasn't dissolved yet, then you have 2 phases. Okay, and you'd have the solid part and then the liquid part. Okay. So most of these you should be familiar with. The ones that you are not or might not be is right here, sublimation, going straight from the solid to the gas state, totally skips over the liquid phase. One example is dry ice. Don't ever touch dry ice with your bare hands. So dry ice is frozen CO2, frozen carbon dioxide, and it's very, very cold. But at room temperature, carbon dioxide is a gas. That's what we breathe out, right? So it goes straight from being a solid ice block essentially to a gas. So that's what's used like for fog machines and stuff, or anywhere you see stuff and it's just kind of the fog is all coming out around Halloween, and so people use dry ice a lot. The opposite process of that is going from the gas state to the solid. We call that deposition. So water vapor can go straight to the ice phase, go straight to the solid phase without passing through the liquid phase. We'll see that sometimes when frost forms, it doesn't actually turn into a liquid and then a solid. It goes straight from being water vapor in the air to being frost on your windshield. Okay. Most of the rest of these you are probably familiar with. There's a small change. You would probably have called liquid to gas evaporation rather than vaporization, but like we talked about already a little bit in the liquid lesson, evaporation or vaporization is the more general term. Evaporation is one kind of that, or you could have boiling, and we're going to discuss that a little more today. Okay, so you have this chart in your book actually, giving you examples of each of these changes of state. When we have a change of state, we are working towards equilibrium. So equilibrium means that we have 2 opposing changes at the same rate, okay, or a balance of these 2 changes. So we reach any change of state, we reach a point where there's no net change in either direction. Okay, and so that's really what we're talking about, like when we're talking change of state, that we reach this point where there's no net change. So here in this example, this is actually vaporization. This is an example of equilibrium vapor pressure. So for equilibrium vapor pressure to really take effect, you have to have a closed system. Okay, so that's why each of these is stoppered. So we put some liquid in our flask here and put a stopper on it. And everything is in the liquid phase. But you can see that some of these molecules are starting to gain some energy. They're starting to evaporate. And so over time, they evaporate and they start to exert pressure because they're moving around. Now they're in the gaseous state, so now they have more energy, they're moving faster, okay? And then eventually you have this, sorry, I need to back up just a little bit. As some of these molecules are becoming gases, some of the gas molecules are condensing back to the liquid phase. And eventually you reach a point where the same number of particles are evaporating as are condensing. That's the equilibrium vapor pressure. Okay, so you have this equal number of particles evaporating and particles condensing, and so you no longer get a net change. Okay, so at that point, that's all that's going to happen. There's no more change that's going to happen. So again, it only happens in a closed system. There are some liquids, so every liquid has its own equilibrium vapor pressure, and that can vary by temperature. So if I change the temperature, that's going to affect the pressure. We'll talk about that a little bit when we get into chapter 11, how the pressure relates to the temperature. But for now, each liquid has its own equilibrium vapor pressure point, but it will change as you increase or decrease the temperature. And that just has to do with the attractive forces and how much energy there is to overcome those attractive forces of being a liquid. So the stronger the attractive forces are, the fewer particles are going to be escaping. Okay. If you have a very low percentage of evaporation, then you have a very low equilibrium vapor pressure. Okay, so it means that they can reach that equilibrium very quickly, just because you're going to have very few particles escaping to begin with, so then very few recondensing. And so you get a low equilibrium vapor pressure. And then there are volatile liquids. Okay, so volatile liquids are the opposite. Instead of having very strong forces holding them together, they have very weak forces holding them together. So they evaporate very easily. That's what we mean when we say readily. They evaporate very easily. It doesn't take much energy at all. And so because they turn into a gas so easily, you end up with a much higher vapor pressure. So they're under a lot more pressure, which tends to make things kind of go like boom, a little easier. Okay, so that's a volatile liquid. Okay, an example that I have actually run into as a mom of vapor pressure is actually this little cup. I loved these cups for the longest time, and then I hated them, and I would never buy them again. So what happens is you put a little bit of your liquid in here, probably milk, because it's a sippy cup for a baby. Yep. And then you end up creating a closed system because you put the lid on it. And as the milk warms up, some of those milk particles become gas, and they start to exert vapor pressure on the remaining liquid, which forces it up the tube. And then you get into that whole like liquid, like the capillary action we were talking about with liquids climbing that narrow tube. And then next thing you know, you got milk squirting out the top and a big old mess of milk all over the table or the floor, wherever it's managed to get to while you weren't looking. So great cups, except for that. But that's because of the vapor pressure. The vapor pressure starts to push on the liquid and force it up the tube. So, I mean, science, it's what it does. All right, so let's talk a little bit about boiling. So we talked about evaporation when we talked about liquids in lesson 2. So evaporation is when just the particles at the surface are escaping into the gas phase. Boiling means that not just at the surface, but particles all throughout our substance are converting into a vapor. Okay, they're all starting to vaporize. And so that usually comes with increasing the temperature. So the boiling point relates to that equilibrium vapor pressure. So the boiling point is when the equilibrium vapor pressure is equal to atmospheric pressure. So we have 3 substances here and their normal boiling point. So normal boiling point means normal atmospheric pressure. Okay. So at sea level is usually what we use. So we're not very far above sea level. I don't know what our elevation is, but it's not much. So water here will boil at 100 degrees Celsius, okay? Because that's the normal boiling point for water. If you go to a really high elevation, like you're in Colorado or somewhere up in the mountains, you can actually boil water at a lower temperature because the atmospheric pressure is less. And so with less atmospheric pressure, you don't have to get the equilibrium vapor pressure as high, so you don't have to add as much energy. So it'll boil at just under 100 degrees Celsius. And it's not much below, but it's a little. And you probably wouldn't even notice the difference, but it does happen. And so that's what it means by the normal boiling point, is at normal or standard atmospheric pressure, the atmospheric pressure when you're at sea level. And so boiling occurs when you get to the temperature where the equilibrium vapor pressure is the same as the atmospheric pressure. Then we are going to talk about freezing. So the boiling point and the condensation point are going to be the same thing. The freezing point and the melting point are also the same point, okay? Because you have equilibrium, you're changing back and forth at the same rate. So freezing requires a loss of heat energy. You have to remove energy as heat. Because if you remember, there's technically no such thing as cold, there's only heat, or the absence of heat. So we have to remove heat from our substance in order to turn it from a liquid to a solid, which is what we call freezing. So the freezing point is actually the temperature where the solid and the liquid phase are in equilibrium. So you'd have just as many particles moving from solid to liquid, melting, right, as moving from liquid to solid and freezing. Okay, so you have an equilibrium there. There's a balance going back and forth. So again, the freezing point and the melting point are the same temperature. Sublimation and deposition would happen as opposite processes, right? So sublimation is going from solid phase to gas phase without going through the liquid phase. So this is how snow can disappear. We don't get a lot of snow here, so we don't have a whole lot of experience with this one. But you can have a snowfall and then the temperatures can still be below freezing, below this by zero, less than 0 Celsius, okay, below 32 degrees Fahrenheit. And the snow can still disappear, even though it's below freezing outside. So you would think it would stay in that solid phase, but it can start to sublimate, okay, or sublime. Okay. And then we've already talked about dry ice. And then deposition is going from gas to solid. Talked about frost. And so those processes, you would be reaching an equilibrium of the number of particles going from one phase to the other and back. Okay, so you have that equal number going from gas to solid and from solid to gas. All right, this is a phase diagram. You have this in your book, and on your homework, it's going to ask you to look at this and answer some questions. So this is a phase diagram. What we are graphing here, we have pressure on the y-axis and temperature on the x. And so it's showing us what conditions we need to have in terms of temperature and pressure in order to have each state of matter. Okay, so this one is for water. So as we increase our temperature, we have to increase the pressure to keep it as a vapor. If you increase the temperature, but you don't increase the pressure, no, I'm saying that wrong. If you increase the pressure without increasing the temperature, you would move from the solid to the, or sorry, from the vapor to the liquid, or vapor to solid, you would be going through deposition, okay, or condensation. Okay, so what we need to look at on here, so it's showing us the conditions that we need for each phase, but it's also showing us the conditions where we would have changes of state. So each of these red lines is describing the change of state. Okay, so, and it doesn't give us all of the numbers on either axis, but that's okay. We don't need them all. But we could use this to predict what, or to determine what pressure we would need at each temperature to undergo boiling, right? To go from vapor to liquid, or to undergo freezing. Okay, so all along this line right here are the temperature and pressure conditions that would send a solid to liquid or liquid to solid. Okay, so it shows the normal freezing point and the normal boiling point. There's a couple other points on here that it shows. This is the triple point. The triple point means that all three states are existing in equilibrium. I'm going to show you that here in just a minute. Okay, so the triple point, we have the same substance in all three states in equilibrium at the triple point. The critical point and the critical temperature and pressure. So the critical point is indicating the critical temperature and the critical pressure. The critical temperature is the highest temperature where we can still have a liquid. Okay, so after that point, no more liquids. If we come back, let me just move myself out of the way again. So for water, the critical temperature is 373.99. If you go to 374 degrees Celsius, you can no longer have a liquid, and it doesn't matter what pressure you have. Okay, that after that point, you're just going to have a vapor. You're not going to be able to have a liquid. The critical pressure is the lowest pressure where that substance can exist as a liquid, okay, at the critical temperature. So the critical pressure for water is 217.75. Okay, so water has to be below a temperature of pressure of 217.75 atmospheres and a temperature of 373.99, or it's going to be a gas. You can't have it as a liquid. All right, here is the video. Move my face out of the way. So this is going to show, and I might skip it through it a little bit. It's not a very long video, but it's showing the triple point of water. So they've sped this up 4 times. So triple point has all 3 phases coexisting. So they put ice water in a vacuum chamber, and then they turned on the vacuum chamber, so they're removing the air, which lowers the pressure. Okay, so if you look at your chart in your book for the triple point of water, or the phase diagram of water, it's a very low pressure and very low temperature that you have to reach that triple point. So as you watch, you're starting to see some bubbles. And so that's the water starting to boil. Notice they haven't added any heat. All they're doing is removing the pressure. So the water is starting to boil at this point. But you still have some ice. You can see the ice in there. It's going to get good and boily here in a minute. Okay, so now we have the triple point. Okay, so we have all 3 phases existing in the same state. And so you're going to see, you'll actually be able to see that the ice is, or the water is melting, freezing, and boiling all at the same time. So you can actually see the formation of ice. And then in other places, you'll see that ice turn back to liquid. And then you have all the bubbles. So this is the triple point of water. Okay, so we're forming kind of a thin layer of ice along the top. And then the ice is still kind of boiling underneath. This is the graph of CO2, carbon dioxide. So you can see the pressure and temperature again. So carbon dioxide has a much lower critical point. Okay. So carbon dioxide at room temperature should be a gas. Okay, so room temperature is somewhere in here. Probably right about here. So you can see the sublimation point down here. So at this point, it's going back and forth between a solid and a gas. Here's the triple point. So you can have, this of course has its own triple point, and then the critical point is way up here. So this is the point at which you kind of no longer have liquid, right? Those are the max conditions for a liquid. Okay. So that's the end of the lesson. You do have a homework to do tonight. And again, it's going to reference this chart here from your book. So you might want to snap a picture of it if you don't want to take your book home, or answer that question first before you go home. And then let's look at your lab a little bit. So you're using the LabQuest. You guys haven't used this year, I don't think. But what you're going to be measuring is the freezing and melting point of water. This is kind of a sit and wait and stare at it lab. You'll have to set up this here. It's going to tell you how to do that. So you're going to be using one of the temperature probes. You're going to set up water and ice. And then you're going to put some more water in the test tube. Okay, and then clamp it to the ring stand. Okay. And then, so you'll just follow the directions of how much water to put everywhere. You'll have to set up the data collection. Okay, so the meter screen is the tab that's on the far left when you're looking at it. Okay, where it looks like a little like analog meter with the thing that goes back and forth. So I don't have anything plugged in, but it's the one where you have the big, usually a big red bar across that's telling you the data. So you have to change your data collection, and then just follow the directions. You're going to have to kind of move. Somebody's going to have to be in charge of moving the temperature probe around. You can take turns with that. That's fine. You just want to continuously, very slightly move it for about the first 10 minutes, and then you'll let it actually freeze into the ice. It's going to stop collecting data after 15 minutes if you set it correctly. And then you're going to analyze your graph that gets produced and store that data. And then you're going to, so the first part is freezing the water. The second part is melting the water. Okay. And you're going to analyze the two graphs and compare them to be able to answer your questions. Okay. Answer all these questions. Okay. So that is the lab that you should be doing next. If you have questions about how to use the LabQuest, Dr. McLaren would be a good choice to ask. She should know where everything is and how to set everything up. All right. If you have questions about the lesson, shoot me a message. The next lesson after this will be on water, and it's the last one for this chapter.